Howdy, guys. Jimmy Song here. Welcome to another episode of Whitepaper Wednesday. I am not sure whether or not I am coming through. So, if you are in the chat, please let me know if you can see me on the screen. At least on my YouTube, it's not showing whether it's not showing anything. It just says this video is restricted. So I don't know if I'm getting blocked or something like that, but if you guys could help me, that would be really, really useful. Okay, so I am loud and clear apparently, and you guys can see me, I guess, and you can see the screen, or I will put on the screen in a second. I just want to go to YouTube. Okay, all right. So it's just a preview window for some reason is not working. All right. So let's just keep going and go to Bitcoin and electronic cash peer-to-peer a peer-to-peer electronic cash system. And as we talked about last time, a lot of this is actually when Satoshi says cash, he's really talking about the fact that there's no intermediary, right? There's no trusted party that you have to use in order to do that, and it's very clear from reading, especially like the abstract and section 1. What we're gonna now do is go through the second half of the white paper, which is section 7 through 12. So that's what we're going to do right now, and let's get started. All right, so reclaiming disk space. Once the latest transactions in a coin, latest transaction in a coin is buried under enough blocks, the spent transactions before it can be discarded to save space. Okay, so what this is talking about is the UTXO model. The fact that a transaction output has been spent means that you don't actually have to keep them around. As long as you know the current UTXO, or the unspent transaction, you don't need to know about its history, right? Like you don't, unless you happen to be interested in that transaction, if it's your transaction, for example, and you're keeping records. But you can actually kind of throw it away, and that's what basically prune mode in the Bitcoin Core software. That's essentially what it does. Is it throws away all of the spent transactions to save disk space. And indeed, the entire blockchain is somewhere around 200 gigabytes. If you just do prune mode, it's like 7 or 8, which is way better. To facilitate this without breaking the block's hash, transactions are hashed in a Merkle tree with only the root included in the block's hash. So the old blocks can then be compacted by stubbing off branches of the tree. The interior hashes do not need to be stored. So this is sort of like going and talking about a UTXO model in kind of like an outdated way, because the way we do it now is basically keep all of the UTXOs in memory and not worry about like compacting anything in the past. But essentially, the purpose of these Merkle trees is that the root hash contains sort of like a fingerprint of all of the transactions that existed before. You hash the transactions, and then you combine the hashes, and you combine the hashes until you end up with one root hash. What Satoshi is proposing here is that if TX 0, 1, and 2 have been spent, then all you need to do is keep this much of the block instead of all of the block, and that could be potentially useful, but we found much better ways to do that. A block header with no transactions would be about 80 bytes. It's actually exactly 80 bytes. If we suppose blocks are generated every 10 minutes, 80 bytes times 6 times 24 times 365 is 4.2 megabytes per year. With computer systems typically selling with 2 gigs of RAM as of 2008, and Moore's law predicting current growth of 1.2 gigabytes per year, storage should not be a problem, even if the block headers must be kept in memory. So, and this is one of the remarkable things about blocks, is that because they're 80 bytes, and I think we're right around 622,000 blocks right now. We're about 8,000 until the halving. It's every 210,000 blocks. But basically, it only grows at like 4 megabytes a year. So you could easily keep it on your phone and in memory on your phone, even if you needed to, because it's like 50 megabytes or something like that currently. that could be very useful, and that could be used to figure out, okay, well, this transaction is in it. Modern nodes, you try to keep all of the UTXOs in memory so you could do fast computation. Essentially, every UTXO that exists, it doesn't take up that much space. A lot of servers, you can have like 16 gigs of RAM or something like that, and you can store all of that in memory and be able to verify transactions and blocks fairly quickly. Simplify payment verification. It is possible to verify payments without running a full network node. A user only needs to keep a copy of the block headers of the longest proof of work chain, which he can get by querying nodes until he's convinced he has the longest chain, and obtain the Merkle branch linking the transaction to the block it's timestamped in. He can't check the transaction for himself, but by linking it to a place in the chain, he can see that a network node has accepted it, and blocks added after it further confirm the network has accepted it. Essentially, this is talking about a Merkle proof, and this was actually not implemented in the original code. It did get implemented as part of BIP37, which I think Mike Hearn and Matt Corallo implemented. But basically, the idea is that the Merkle root has information, or is sort of like a fingerprint of all the transactions. And if you have the right fingerprints, you can prove that this transaction is part of this Merkle root. You need this hash, and you can combine it all the way and get the Merkle root. And that gives you proof that this transaction was inside this block. Now, there are vulnerabilities which we found out since then, but the idea here is that if it's in this header, then there can be a proof that this transaction was in this block, and you only need to keep the 80-byte header and not the entirety of that block, which could be like a megabyte or something like that. So that way you can get proof, and you can have simplified payment verification. So if you're getting paid money, essentially, and your transaction was included in a block, a node can prove to you, hey, your transaction was included in the block by giving you proof. As such, the verification is reliable as long as the honest nodes control the network, but is more vulnerable if the network is overpowered by an attacker. While network nodes can verify transactions for themselves, the simplified method can be fooled by an attacker's fabricated transactions for as long as the attacker can continue to overpower the network. One strategy to protect against this would be to accept alerts from the network nodes when they detect an invalid block, prompting the user software to download the full block and alerted transactions to confirm the inconsistency. Businesses that receive frequent payments will probably still want to run their own nodes for independent security and quicker verification. So the idea of like just sort of like accepting alerts and stuff like that, it's kind of implemented in compact filters and what you would call neutrino. Essentially, you download the entire block whenever you see a transaction. Whenever you see a transaction, your transaction might be included in that block, and that's using Goulam coded sets and like essentially a fingerprint of the transaction that's even smaller to detect whether or not it might be in that block. And then if it might be in that block, you download the whole block and see if any of them are yours. That's how it works. Combining and splitting value. Although it would be possible to handle coins individually, it would be unwieldy to make a separate transaction for every cent in a transfer. To allow value to be split and combined, transactions contain multiple inputs and outputs. Normally, there will be either a single input from a larger previous transaction, or multiple inputs combining small amounts, and at most two outputs, one for the payment and one for returning the change, if any, back to the sender. It should be noted that fan out, where a transaction depends on several transactions and those transactions depend on many more, is not a problem here. There's never the need to extract a complete standalone copy of a transaction's history. All right, so what this is talking about is really the part of the UTXO model. Essentially, every input can have any amount value, right? It could be 1 Satoshi, it could be 30 Bitcoins. It doesn't matter. The outputs can have any value. That way, you don't need like sort of bills like you do with cash, where you have a $100 bill, and if you want $123, you need 100, a 20, and 3 ones. Instead, what you can do is have one output. Essentially, the UTXO so has a value assigned to it, and it could be like 123 bitcoins instead of like five pieces of paper. You have one UTXO, and that can be a very good thing. Now, what Satoshi gets wrong here is at most two outputs: one for the payment, one returning the change if any, back to the sender. I don't think Satoshi really thought about sort of being able to send to lots and lots of people at the same time, which is essentially what every exchange that's using batched outputs uses. All right, privacy. The traditional banking model achieves a level of privacy by limiting access to information to the parties involved and the trusted third party. The necessity to announce all transactions publicly precludes this method, but privacy can still be maintained by breaking the flow of information in another place, by keeping public keys anonymous. The public can see that someone is sending an amount to someone else, but without information linking the transaction to anyone. This is similar to the level of information released by stock exchanges, where the time and size of individual trades, the tape is made public, but without telling who the parties were. So the traditional privacy model involves identities, transactions, trusted third party, counterparty, public. And this line is basically where the wall is between the public and everybody else. The new privacy model is that the public knows all about every transaction, but identities are hidden because the public key and identity are not strongly linked, like in the traditional model. As an additional firewall, a new key pair should be used for each transaction to keep them from being linked to a common owner. Some linking is still unavoidable with multi-input transactions, which necessarily reveal that their inputs were owned by the same owner. The risk that if the owner of a key is revealed, linking could reveal other transactions that belong to the same owner. So this is sort of anticipating chain analysis, which is essentially this technique of figuring out, okay, if the inputs are spent together, then we know that those belong to the same person. And this is what CoinJoin attempts to foil by having inputs that are not that are not owned by the same person or a group of people to put them into the same transaction. A new key pair should be used for each transaction to keep them from being linked to a common owner. And this wasn't really used that much early on. People reused addresses and so on. But with BIP32, this came much more into being. Calculations. We consider the scenario of an attacker trying to generate an alternate chain faster than the honest chain. Even if this is accomplished, it does not throw the system open to arbitrary changes, such as creating value out of thin air or taking money that never belonged to the attacker. This is a very important point. No matter how much of the hash rate that the attacker has, it does not allow them to inflate the currency or take money that doesn't belong to them. And these are two essential security properties of that Bitcoin has as a result of like basically many nodes being run. Nodes are not going to accept an invalid transaction as payment, and honest nodes will never accept the block containing them. An attacker can only try to change one of his own transactions to take money he already spent. So this is basically describing the 51% attack. You can't 51% attack with somebody else's coins. You can only do it with your own. So essentially you pay somebody and then take that money back. That is the only thing that attackers can do. But of course, if that happened and the person that received it required three confirmations or something, you need to do at least 4 blocks worth of work right away, which would be very, very difficult. And that's sort of the economic incentive at play here. The race between the honest chain and an attacker chain can be characterized as a binomial random walk. The success event is the honest chain being extended by 1 block, increasing its lead by +1. And the failure event is the attacker's chain being extended by 1 block, reducing the gap by -1. The probability of an attacker catching up from a given deficit is analogous to a gambler's ruin problem. Suppose a gambler with unlimited credit starts at a deficit and plays potentially an infinite number of trials to try to break even. We can calculate the probability he ever reaches break even, or that an attacker ever catches up with the honest chain, as follows. P, probability an honest node finds the next block. Q, probability that the attacker finds the next block. QZ, probability the attacker will ever catch up from Z blocks behind. So this is the equation, and this is a well-known problem, like within combinatorics or whatever, and it's called gambler's ruin because gamblers have a tendency to do something like this, which is, that, house has the edge. But if you're behind, you try to catch up, despite knowing that on average you would keep losing money. And this is basically describing that. Given our assumption that P is greater than Q, the probability drops exponentially as the number of blocks the attacker has to catch up with increases. With the odds against him, if he does not make a lucky lunge forward early on, his chances become vanishingly small as he falls further behind. So as long as the majority is honest, it makes it harder and harder for an attacker to cheat and double spend. We now consider how long the recipient of a new transaction needs to wait before being sufficiently certain the sender can't change the transaction. We assume the sender is an attacker who wants to make the recipient believe he paid him for a while, then switch it to pay back to himself after some time has passed. The receiver will be alerted when that happens, but the sender hopes it will be too late. And this is the essence of a double spending attack: is you pay someone, get whatever you're hoping to get in exchange, and then you take the money back. And it requires enormous amounts of hashing power, and the probabilities are being discussed in this part of the paper. The receiver generates a new key pair and gives a public key to the sender shortly before signing. This prevents the sender from preparing a chain of blocks ahead of time by working on it continuously until he is lucky enough to get far enough ahead, then executing the transaction at that moment. Once the transaction is sent, the dishonest sender starts working in secret on a parallel chain containing an alternate version of his transaction. The recipient waits until the transaction has been added to a block and Z blocks have been linked after it. He doesn't know the exact amount of progress the attacker has made, but assuming the honest blocks took the average expected time per block, the attacker's potential progress will be a Poisson distribution with the expected value. To get the probability the attacker could still catch up, now we multiply the Poisson density for each amount of progress he could have made by the probability he could catch up from that point on. Rearranging to avoid the summing the infinite tail of the distribution, converting to C code, running some results, we can see the probability drop off with exponential Z. All right, so let me explain this table. 10% of the network hash rate. Catching up one block is about a 20% probability. 2 blocks is 5%. 3 blocks is 1%, and it gets way less, and so on. With 30% of the network, it drops from 17% at 5, and like at 10 blocks, it's like 4%, and so on. For solving for P less than 10, it's basically, if you, P less than 0.1. So basically, you want less than a 0.1% chance that someone could catch up. You would need, for 10% of the network, you would need 5 block confirmation. For 15%, if an attacker has 15%, you would need 8 blocks of confirmation. 20%, 11 blocks, and so on. 45%, you need like 340 blocks, which is a lot. All right, conclusion. We have proposed a system for electronic transactions without relying on trust. We started with the usual framework of coins made from digital signatures, which provides strong control of ownership, but is incomplete without a way to prevent double spending. To solve this, we proposed a peer-to-peer network using proof of work to record a public history of transactions that quickly becomes computationally impractical for an attacker to change if honest nodes control a majority of CPU power. The network is robust in its unstructured simplicity. Nodes work all at once with little coordination. They do not need to be identified since messages are not routed to any particular place and only need to be delivered on a best effort basis. Nodes can leave and rejoin the network at will, accepting the proof of work chain as proof of what happened while they were gone. They vote with their CPU power, expressing their acceptance of valid blocks by working on extending them and rejecting invalid blocks by refusing to work on them. Any needed rules and incentives can be enforced with this consensus mechanism. So, essentially, this is all Satoshi deeply thought about Bitcoin because there's a lot of things that I'm you get the sense that Satoshi really thought about it because there's a lot of stuff that was anticipated. Reclaiming disk space. This is the UTXO model. Incentives, simplified payment verification. chain analysis, splitting and combining value, privacy, the different privacy model, calculations on double spending attacks. Essentially, a lot of it was anticipated, and it was really, really well done. So anyway, that is about it. I hopefully this helps you. If you are wanting to learn more about Bitcoin, you can always go and check out my books. Programmingbitcoin.com has a link to all of the stuff that I do. But yeah, you can order Programming Bitcoin. It's on Amazon for like $45. The Little Bitcoin book is also on Amazon. It's available for the Kindle. You can get it on audiobook, but it's all there as well. All right, let's see if there are any questions. How about them quantum computers? Is there any hope if they become a reality? They're not going to become a reality. If they do become a reality, it's going to be very limited, and it's not going to have enough qubits to break Bitcoin. So that's about it. Fiat delenda est. This song is done.